switching fabric. And specifically, some messages, they require the switching fabric to guarantee that it delivers them in order, which simplifies the protocol, but makes the interconnection network somewhat more complicated and more difficult to verify. Okay, it also isn't clear whether they support all memory models. As far as I know, they do. But otherwise, they pretty much have achieved the goals that we set out to meet in 2001. Okay, so this is the slide that I used to, well, here I'll summarize what I described quickly in my tutorial along the way. But a MESI protocol is, there are a number of variations of it, but the generic MESI protocol, the name MESI derives from the fact that there are 4 possible states that a cache line might exist in each cache that is invalid, which is to say either the cache line is not there at all, or it's received an invalidation signal which says the copy that you have may be stale, so you should not actually use it. The reason it may be in that state is because when it gets invalidated, you don't necessarily throw it out right away, but you might actually be able to take advantage of the fact that you are interested in that cache line, and you might, for example, when you see somebody else read it shared, you might want to grab it and put it in your cache. The shared state is a state that says, I have a copy, I can read it, others may have another copy, I don't know whether anybody else does, but I cannot write it without first making sure that all the other copies have gone away. The modified state says I've done that, so I have the only copy, and I've written it, and it's different than main memory, which says if I throw it out of my cache, I actually have to write it back to main memory. Of course, if anybody else tries to read it or write it, I have to respond and intervene, making sure that memory doesn't supply stale data. And finally, there's the exclusive state, which is actually an optimization set, which says I have requested and received the right to modify this line. I have the only copy in the system, but in fact, I haven't written it yet, so it's the same as the copy in main memory. This is a very desirable state to begin, because that says you don't have to notify anybody to do anything. You can modify it, just change the state to modified. You can throw it out of your cache because the copy in main memory is correct. And of course you can read it and write it. So it's great. You'd like every cache to be, entry in every cache to be an exclusive state, but of course you can't, because once it's written, it goes from exclusive to modified, and when somebody else tries to read it or write it, you have to change that state as well. So that's where you'd like to be. Just mention for generality that there's a slightly broader description that includes a 5th state called own state, which results in what's called a MOSI protocol. I won't talk about that, but many of you will be familiar with that, and I'm mentioning it primarily to acknowledge that it does exist. We developed a 5th state as well for somewhat different reasons, although it's similar in many ways to the own state. And we called it a forward state, so we have 5 states that we call the protocol MESI as opposed to MESI. So our protocol, in fact, we called the MESI protocol, or MESI, as my co-author liked to refer to it. So I will describe that with some slides. Now I mentioned snooping, I mentioned directories. The directories were first proposed in 1976, actually, as a new idea for cache coherence. And ever since the 70s, they've been the future. The next thing, people have been predicting for a long time that they will come, that snooping caches will die, and the future will have to be these directories. So far, there have been a few minor successes. SGI, for example, built systems for a number of years that have directory-based cache coherence protocols. But the dominant player